All right, so this is section 3, and it's going to start into our shortcut rules for derivatives. So this is something you should be looking forward to. We're not going to have to look and go through that entire long process of solving the difference quotient and the limit to find a derivative anymore. We're going to have some shortcuts that we can work with. All right, if the derivative of a function is its slope, then a constant function, which is a horizontal line and has a slope of 0, then the derivative must be 0. So there's our first rule. The derivative of any constant is equal to 0. For example, if we have y equals 3, that's a horizontal line, the slope is 0. Y prime equals 0. So the derivative of any constant we have is 0. One of the things that a lot of people will get thrown off by, they'll see something like pi squared and think, oh, well, pi is a variable. Actually, it's not. It's a constant. It's 3.1415926, etc. But if you square it, it's still a constant. So the derivative of pi to any power that's not x is going to be 0. All right, now if we find derivatives with a difference quotient, you don't have to write this down in your notes. Just kind of follow along with it, and it's going to lead us to our next step, our next shortcut. If we had the derivative with respect to x of x squared, we would get this, and when we solved it out, we ended up getting 2x. All right, if we did x cubed, we would do very much the same thing. We could actually use Pascal's triangle to expand our x plus h cubed. But when we cancel things out and everything, we still are going to just get 3x squared. And when we take the derivative of x to the fourth, using Pascal's triangle again here, to expand the x plus h to the fourth power, we're going to get x, we're going to get all this. I'm not even going to talk through it. And all that stuff's going to cancel out, and we're going to be left with 4x to the third. So hopefully you observe a pattern. The derivative of x squared was 2x. The derivative of x to the third was 3x squared. The derivative of x to the fourth is 4x to the third. The derivative of x to the fifth is 5x to the fourth. The derivative of x to the sixth is 6x to the fifth. This leads us to the power rule. So if we're taking the derivative with respect to x of x to some constant power, all you're going to do is you're going to bring that number out front and subtract 1 from the power itself. So just like the one we saw here just a second ago, x to the fourth, shortcut rule would bring the 4 out front, subtract 1 from the 4, so you end up with 4x to the third. If we have y equals y equals x to the 8th, we're going to bring the 8 out front and subtract 1. So we end up with y equals 8x to the 7th. And like I said, this is known as the power rule, and it's one of the ones that you're going to use more than anything. All right, we also have the constant multiple rule, and it says that if you have some constant number that's multiplied by some function that you're going to take the derivative of, you can just tag along that constant. It just moves down. So for instance, if I have the derivative of c times the function u, it's the same thing as c times the derivative of u with respect to x. I don't actually have to take the derivative of the c. It just tags along. Now, this actually is part of another rule we're going to talk about in a second called the product rule. This is a special case for the product rule in that the other term, the second term, is going to go away because when we take the derivative of the c, it's 0 and everything else is negligible. It goes away. Anyway, just remember, if you have something like this, cx to the n power. Notice the c just tags along. The n x to the n minus 1 is just the derivative of the x to the n. Nothing else changes. The c doesn't change. Now, when we use the difference quotient, we observed that since the limit had no effect on a constant coefficient, we could just move that thing all the way out to the front. So it was smaller numbers we were dealing with, and we did not have to have such large numbers. We could just bring the constant that was common to everything out in front and outside of the limit. Same idea here. All right, if we had the derivative with respect to x of 7x to the fifth, notice the 7 just tags along, and I take the derivative of x to the fifth like I normally would. So I get 5x to the fourth. Now I can multiply these numbers out front, the coefficient of the 5x to the fourth and my constant multiple of 7, and you get 35x to the fourth. So that's the constant multiple rule. All right, we also have the sum and difference rules, which says that if we take the derivative of u plus v, function u plus function v, it's nothing more than the derivative of u with respect to x plus the derivative of v with respect to x. Notice the sign here and here stayed the same. The only way that's going to change is if the dv dx is a negative. That would change this sign to a minus. And you have the exact same rules with subtraction. Derivative with respect to x of u minus v is the derivative of u with respect to x minus the derivative of v with respect to x. So with this one right here, essentially what this tells us we can do is we can take the derivative in parts. Take the derivative of this and take the derivative of this separately, and then just keep the sign in between them. So y prime here is going to be 4x to the third plus 12. So you're essentially treating each term separately as you take your derivative. All right, let's look at an example over here. We've got 3 terms now. Still doesn't change a thing. What's the derivative of x to the fourth? It's 4x cubed. Derivative of negative 2x squared will be negative 4x, and the derivative of 2, derivative of a constant is 0. So we end up with 4x cubed minus 4x. All right, so let's find the horizontal tangents of that x to the fourth minus 2x squared plus 2. Now, if you remember, horizontal tangents mean that the slope slash y prime equals 0. That's where our tangents are horizontal. So we need to find out what y prime is. So y prime, which we just found, was 4x cubed minus 4x, and we're looking for where that thing is equal to 0. Well, we've got a common 4x we can take out, and then that's going to leave us with x squared minus 1. So we've got a value where x equals 0 is going to make this thing 0, and then this would factor into x's plus or minus 1. So x equals negative 1 and positive 1 from that part. So our solutions here are places where our horizontal tangents are 0, negative 1, and 1. Now it says find the horizontal tangents. It doesn't say find where they are. This is where they are. We need to find what they are. Well, what they are is going to be the y value. Remember, a horizontal line is y equals something. So we need to find out what y is when x equals 0, when x equals negative 1, and when x equals 1. So y equals, let's say y sub 0. That means we're going to plug in 0 to the fourth minus 2 times 0 squared plus 2, which gives us 2. So that gives us a y equals 2 as the horizontal tangent at x equals 0. And then what about with the negative 1 and the positive 1? Well, right here, notice squared and fourth, if they're even powers, does it matter whether this thing is negative or positive? No, we're going to get the same exact answer for both of these. So y of 1 is going to be 1 to the 4th power minus 2 times 1 squared plus 2. So here we're going to get 2, here we're going to get, here we're going to get negative 2, here we're going to get 2, and then we're going to get 1. So y equals 1 is our other tangent. Now you can plug in the negative 1 if you want to, but negative 1 to the 4th is still going to be 1. Negative 1 squared is still going to be 1 to give me a negative 2 there. So you're going to get the same answer. So my two answers here, my two horizontal tangents, are y equals 1 and y equals 2. So those are my horizontal tangents. Now let's look at the graph. And there is what the graph looks like. So here we can see we've got a horizontal tangent that would take both of these parts out and one that would take that one out. So there's your y equals 2, there's your y equals 1. And in case you're curious, there is the derivative, there's the graph of the actual derivative value. So notice here where it has a minimum, we've got a function value for our derivative that's equal to 0. Right there, same thing. Right here, same thing. Things to think about. So the first derivative, the slope, is 0 at those 3 points, those 3 values of x that we found in the on the previous page. All right, our next rule is the product rule, and it says the derivative with respect to x of u times v, where u and v are functions, not just constants, is going to be u times dv dx plus v times du dx. Now, another way that you can remember that is first times the derivative of the second, u times dv dx, plus second v times the derivative of the first, du dx. So that's right here. So first times the derivative of the second plus second times the derivative of the first. Now if you get these confused because of that plus, it's not going to make that big a difference. But you need to make sure that you get this rule down. Notice that this is not just a product of the two derivatives like the sum and difference, or sum and subtract, sum and difference before. Sum and difference rules were, if you just take the derivative of u and multiply it times the derivative of v, you're getting the wrong answer. There is a special case here you got to make sure you follow it. Alright, so with this one, if we were going to take the derivative, what we would do is first, so x squared plus 3 times the derivative of the second is going to give us 6x plus 5, 6x squared plus 5, and then plus 2x cubed plus 5x times the derivative of the first, which would be 2x. All right, and then you could actually combine some stuff and all that. We're not going to worry about that. I'm just going to show you how it would come up. Actually, nope, that's not even what I'm doing here. Let's look at both of them, and I'll explain it in just a second. So here they're doing the product rule, like I was just showing you. There it is. And then when they simplify all this out, you're going to get 6x to the 4th plus 5x squared plus 18x squared plus 50. Simplify it down. 10x to the 4th plus 33x plus 15. 33x squared plus 15. Now over here, notice that they FOILed this out right here first and got this. Then they took its derivative once they simplified it down, and notice they get the same thing. So if you've got a nice little polynomial thing here, you don't have to use the product rule. You can always multiply and simplify that thing out first. All right, and then we've got the quotient rule. And the quotient rule is memorized as this: bottom times the derivative of the top minus top times the derivative of the bottom over bottom squared. Now, a little quicker way of saying it is bottom d top minus top d bottom all over bottom squared. This one's a little more complicated. You're not going to like it. And guys, you don't have to FOIL out the bottom or anything like that. If you got things that cancel out, that's great. If you don't, that's great too. All right, so with a situation like this, we would do bottom times the root of the top. So you got x squared plus 3 times 6x plus 5 minus top times the root of the bottom, which would be 2x. Notice that that's very, very similar to that product rule, except for that we got a minus in between there. And then over the bottom squared, which is x squared plus 3 quantity squared. And then, of course, you probably want to simplify a little bit on top, FOIL this out, distribute this, combine any like terms, but you don't always have to do that. Most of the time when you're going to have to do that and simplify that down is when you're going to have a multiple choice question, and they're going to have it somewhat simplified. With a free response question, you could have stopped right there and you're perfectly okay. All right, now higher order derivatives, we can take the derivative of a function over and over and over and over again, and we get the derivative of the derivative, the derivative of the derivative of the derivative, etc., etc. You get the idea. So if y prime equals dy dx is the first derivative of y with respect to x, we can take its derivative, the derivative of y prime with respect to x, and we're going to get y double prime, or d squared y over dx squared. These are the two ways that you're going to note the second derivative. All right, and then you can take the derivative of the second derivative and you're going to get the third derivative, y triple prime, which is nothing more than the derivative of y double prime over x, over dx. This is what we're doing. This is what we call it. Now, when you get to the fourth derivative, notice they stopped doing the primes out here, and it's the 4 in parentheses. That is signifying y to the fourth prime, or the fourth derivative of y. And all the fourth derivative of y is the derivative of the third derivative of y. Now, depending on what function you start off with, these different derivatives will have different meanings. We'll talk about position function later, and if y is the position function, then y prime is the velocity, y double prime is the acceleration. So we're going to learn things about how to apply these multiple derivatives. All right, so that's all of section 3.